Sasha Shnirelman from Montreal. And I think Steve will. What's the title, Sasha, exactly?
Title was right 2-point problem. For the, say, 2D Euler equations.
Right. Well, I'll see if we can get the screen. You have it on the computer, or?
I have just Blackboard.
Blackboard. Ah, very good.
Greenboard.
Excellent.
Greenboard.
That's true. I was a bit confused by that. Okay, so welcome.
Okay, thank you. Let me begin from the beginning. I'll formulate the problem and then tell what I know about it. So I first thought that I have solved it, but now I see that it reduced to some other problem which is interesting by itself. So I'll try to tell it as much as I will be able. So consider the motion of ideal incompressible fluid. Yeah. So I consider it motion in two-dimensional case, and to be say concrete in the whole talk, suppose that our flow domain is two-dimensional Tor. So the fluid is moving along the two-dimensional Tor. It is described by the well-known equations du dt u gradient u plus gradient p is 0, and u dx is 0. I confine myself to this motion which do not move the center of mass. Or the corresponding Lagrange equation d2. So we consider ft m to m. It is a flow map which moves every fluid particle from initial position to its position at the time t. Yes, and ft double dot plus nabla p times ft is 0, so it's the second Newton's law, and I would write that the ft dx, the Jacobian, is identically 1. So this is incompressibility. And center of mass is fixed. Yeah. So these are the I called Lagrange equation, and these are the Euler equation. They are equivalent. If we consider sufficiently regular solution, then these are describe the same flow. And now, so given v, initial velocity, so ut u of xt, solution of Euler equation with u x0 is v of x. Yes. Then we have gt, solution of Lagrange equation with initial conditions. G0 is identity map, so we start from every point from where it was, and gt dot is v. Yeah, and now consider g. We know that if u is or v is initial velocity is regular enough, then solution exists, unique, and for regular as initial condition. So this is true. And in particular, we are interested in G1. G1 is a position which the particle will assume at time 1, G1 of x. And I denoted by exponent of v. Yeah? So gt is a solution of the following equation. D gt of x dt equals u of gt of xt. Yes. So this is just notation, exponent. There is another exponent. This may be called geodesic exponent. There is also group exponent, which satisfies the following. It is exp of v. It is a solution of the following equation: dht dt equals v ht of x. Yes, so we fix the point ht and move along the this field. Yes, it is the exponent. This exponent I don't consider here. It has completely different properties. Yeah. Now, let me introduce notation. D equal all fluid configurations. Diffeomorphism M to M such that they incompressible and center of mass is fixed. Yeah. So this is a group of such diffeomorphism, and V is the set of vector field V of x such that V is 0, integral V dx is 0. So this is, so to say, infinite dimensional Lie group, and this is Lie algebra. Yeah? And the question is the following. For any V from the Lie algebra, for any initial velocity field, we have its exponent, which is defined this way. So it is the position of the fluid particles after time 1. If the fluid is pushed initially with velocity field v. Yeah. So and by the basic theorems, it is a good map. It is defined. So the question is, can any fluid configuration, any fluid position be obtained by this as a value of exponent? So the question is it true that x of all v is all d? Yeah. So given a fluid position, can we push the fluid so that after time 1 it assumes exactly this position? So this is exactly what is a 2-point problem. So, or no. Yes, this is what I ask. And the most probable result is yes, it is true. Yes, so conjecture, for now it is conjecture. Yes.
Can you define what this exponent is? Is this like a series or what is it?
Exponent is just notation. So for any given vector field V, I consider solution of the Euler equation, u of xt with this initial condition. Then I integrate this time-dependent vector field. So starting from point x, we move and come to the point, say, g of x, that after time 1, g1 of x. Okay. Yes? So this is correspondence between
of exponent.
Correspondence between initial velocities and final configuration. And this is denoted, it is a just notation exponent.
But there's a reason it's called x, because when you solve it, you have a vector field, it's exponential.
Reason for what?
There's a reason you call it.
I'll explain it is in the next 5 sentences. Yeah. So,
So you take an initial condition,
yes,
the corresponding solution of the Euler equation,
yes.
and this is the displacement field.
No, displacement position. Displacement is the vector connected, x and g of x. Yes, so it is just position.
I see.
Position. Yes. So d, we can introduce some metric in V, namely Riemann metric in V. Vw is integral over m dx w of x dx. So it's just a L2 metric. Yes, and then if we have the vector, the family GT, the family of diffeomorphism, it is flow or curve in D. We denote L of GT, say from 0 to 1, equals integral from 0 to 1, GT dot square root dt. It is just like in the usual Riemannian geometry. Yes. So square root of kinetic energy is integral square root of kinetic energy is just the length, and then equation the Lagrange equation or the Euler equation, which is Lagrange equation displaced to algebra Lie, is the geodesic equation. So solutions of the Lagrange equations are geodesic indeed. No, with respect to this metric. Yeah, and so our question now is we have initial point. No, initial position is identity. This means that every point is exactly where it is its reference point. Yes, and then we have initial velocity v, and then we have this geodesic gt. Yes, and then find the point g1, the end point of the geodesic for time 1. Yes, and this map So V which is tangent space to D at the point identity. Yes? And this map from tangent space at some point onto the whole manifold is exactly what is called in differential geometry exponential map. No, geodesic exponential map. Yes? So this is defined for any Riemannian manifold, unlike the group exponential, which is defined just for Lie group, which is defined different. It is one parameter subgroup. And this is what we are studying. So hence the name exponent. It is just node to differential geometry. And our problem can be formulated as follows. Given G in D, find a geodesic GT connecting G0, which is identity, and G1, which is G. So we have 2 points and try to find a geodesic which connects them. Yeah? So this is why it is called 2-point problem. Yeah? Okay.
Do you need your space to be dense in geodesics?
Excuse me?
Do you need your space to be dense in geodesics, or it's irrelevant?
I will tell you all. So I remind you the Hopf-Rinow theorem from differential geometry. Suppose that M is a finite dimension Riemannian manifold. Suppose that any geodesic GT in M can be continued as a geodesic for all real t. So all geodesics can be continued to infinity in both directions. Then for any G0, G1 in M, there exists a geodesic GT connect them. So it sounds very similar to what is said here. We have 2 points and are looking for a geodesic which connects them. Yeah. So in fact, this theorem has little to do with our problem and helps very little because how this theorem is really proved. We have 2 points, G0, G1, and consider all the lines connecting them and try to find the shortest one. Yes, and using this condition after some simple reasoning, we prove that yes, the shortest one exists, and being shortest, it is automatically geodesic. So it is, and it depends on the continuous condition that M is finite dimensional, so its sphere is compact. Yeah. So using some simple compactness reasoning, we find this shortest line. So what happens in this case for a group of diffeomorphisms? First of all, it is not locally compact, so all the reasoning failed. Second, the result is also not true, because for some pairs of fluid position or initial and some other, there is no shortest way. So the minimum is not achieved. Yeah. So we cannot find the shortest curve connecting two points, and if we try to find it, say construct some minimizing sequence, then it will converge to something which is say discontinuous flow. Yes. Let me spend a couple of minutes to give corresponding example, because it is remarkable in itself. So consider a flow which is given by its stream function psi of xy, yes, such that u psi of x 1 x2 u1 is minus dψ dx2, u2 is dψ dx1 on the torus, and psi is the following: psi x1 x2, it is example, equals sine mx1 times sine nx2. Yeah. Here we can take any m and n, and I choose m which is much less than n, and this much less m much more than 1. Yes. So what happened? It is a remarkable flow because it was used by Arnold first to prove that the curvature of the group of diffeomorphism can be positive in some directions. Yeah? Then this same flow was used by Messiolic to prove that along this flow there exist conjugate points. Yes, and now it turns out that this flow is such that if you take two sufficiently remote points on this geodesic, by the way, this is eigenfunction of Laplacian, and hence this is a steady solution of Euler equations. Yeah. Now suppose GT is corresponding ponic geodesic. Yeah. So how it looks? The domain, the torus, is divided into long and narrow rectangles like this. No, they are equal. In each rectangle, we have some flow with closed flow lines. Yeah. Like this, and so on. What can be the strategy to find the shortest way between G0 and G1? G0 is initial position. G1 is what happens after time 1. Or maybe not 1, but some t which is large. So what is, how can we see that this is not the shortest way, how it was seen? No, if we take one rectangle separately, we can make it closer to the disk, for example, make it a square, yes, or even better, make it a hexagon, yes, and take the flow in this polygon, which is conjugate to the flow in this rectangle, yes, and it's clear that the energy of the conjugate point in this in the square is smaller than in a long rectangle, because we have no, here in this rectangle we have to go forth and back for a long distance, and here we are moving more or less around the circle, yes, and so the true minimizer will look as follows. We first cut this domain along the boundaries of this rectangle, and then we organize somehow a flow discontinuous along these lines, so that after in the end of this process we'll have this hexagonal system of polygons. Then the flow will make necessary number of revolutions in each of these polygons, and then it will be moved back to original positions. Yes, and this is this is how the minimizers look here. So minimizer is not, it exists, but it is a minimizer in a weak sense. It's not a diffeomorphism, flow of diffeomorphisms. Yeah. Now, what is the status of this example? I would say that it is not proved correctly, but it is based on some numerical simulations, which were, I think, started by Conrad and continued by some other people, including my student. So they show in this direction. So in this case, for this example, we have one geodesic, which is definitely a geodesic. It is this steady flow on one hand, but it is not a shortest way between 2 points, if the points are not very close. And if we look for a shorter one, the minimum is not achieved, and this minimizing sequence goes straight to some already non-regular flows, discontinuous flows. Yeah? So this is a clear case of appearance of discontinuities. If we can interpret it this as follows. Consider corresponding magnetic problem. Suppose that our domain, three-dimensional domain, is a long tube, yes, and we consider magnetic fields, yes, tube which is filled with mercury, for example. Consider magnetic fields which are going more or less parallel to the axis, so paraxial magnetic field, which is fixed by, say, conducting flux in the end points, and we are looking for a minimizer of magnetic energy in the among these paraxial fields. Yes, in this approximation. Then it will be the variational problem identical to the problem of minimizing the length of this flow on the group of two-dimensional diffeomorphism. And what I said says that here will appear current layers, which is known use for astrophysicists.
What if it is electric field?
Excuse me?
Why is it important that it's magnetic field and not electric?
Because the very problem is, I think there is no electric problems which is similar to magnetic, because magnetic and electric fields are not perfectly symmetric.
No, I understand, but in this argument about minimizing energy, why is it?
We need some we need some medium which so that electric field is frozen in it. So it should be a medium with very high magnetic permeability. Yes. So if we have such supermagnetic, yes, then it will be true for electric field. Yes, but such supermagnetics are what close to supermagnetic become solid. So we don't have liquid supermagnetics. And we have liquid good conductors, like mercury. Okay, so we need some other idea to how to prove this existence of. So in this case, which I told you, there definitely exists a minimizer, a geodesic, which we started from the beginning from geodesic. Yes, but this geodesic is definitely not minimal. Yeah. So this hints that in general we always have a geodesic, but sometimes it's minimal, sometimes it's not. Yeah. So we have to find a construction of geodesic which is independent on the minimizing property. Yeah. So other principles. So now I want to explain how it is doing, how it is done.
Can I just ask you about these magnetic fields again?
Yeah.
Did I understand correctly that there is no fluid there, just magnetic field?
No, I said that it is a fluid,
Oh,
like
there is a fluid.
Like mercury.
Okay.
Yes, well conducting and incompressible fluid.
Fine. So you say there will be discontinuities developed?
Yes.
Well, are you going to violate divergence of B equals 0 or not?
No.
You are not. So discontinuities are such that there is no monopoles.
No, without, because it is just
Closed lines.
the field is tangent to the surface of discontinuity. So it doesn't violate. Yeah. No. Now I want to specify, which I had to do from the beginning, the functional space, regularity class of the vector fields and diffeomorphism. So suppose V is Sobolev space, and G also in a Sobolev space. No, I mean in local coordinates. So the set of such V in HS V capital is called Vs, and the set of such G HS D I call it Ds. Yes, and S should be sufficiently high, say more than 3 in this case. And then we have this map X from Vs to Ds. So these are two, this is a linear space, this is an infinite dimensional manifold. It is Ds smooth, say Hilbert manifold. Yeah. Now the main idea is that there exists some stronger, more rigid structure in this group of diffeomorphisms, which makes the things much better.
So is X is continuous, smooth?
Excuse me?
How regular is X?
X is infinity.
Is infinite.
I would say analytical. Yes. So X is finite was proved by Eben and Marsden. It is a classical result. So it is an analytical map, and the question is whether it is onto the whole manifold D or not. Yes. So it is known that the topology of infinite dimensional Banach-Hilbert manifolds is much worse than finite dimensional. In particular, it is without additional conditions, it's impossible to use some topological method, say principle of fixed point or principle of preservation of area, which work quite well in finite dimensions. So we require some additional properties. And here I propose some set of additional properties which are really satisfied here. So let me explain these properties. Suppose we have x and y, even a Banach space. And x prime, y prime, also Banach spaces. So x embedded in x prime, y embedded in y prime, they are the images. So embeddings are compact embeddings. With dense images. No, we can example HS minus 1, something like this. Suppose we have nonlinear, no, generally operator f from x to y is continuous map. And suppose that f has the following property. F of u is, say, phi u of u, where phi u is an affine map from x to y. Affine means linear non-homogeneous, linear plus shift. And u is continuous from x prime to affine of xy. So such map is called A is called quasi-linear. Quasi-linear map.
F is called, or A?
Excuse me?
F or A?
F. Quasi-linear map. Yeah. No, quasi-linear reminds us about quasi-linear differential operator, such that non-linear differential operator, which is linear with respect to highest derivatives. But let me show that I would say all operators, no, more or less all operators which are useful in analysis belong to this class. So let's consider example. x equals y hs on R1. And the map f u of x goes to f of u of x. Yeah. So now let me transform it. F of u of 0, integral from 0 to 1. Let's differentiate f prime u of t, u prime of t dt. Yeah, I'm sorry, f c infinity function. Yeah, equals say phi u of u at the point x, where phi u of v of x is f u of 0, integral 0 to x, f prime of u of t, v prime of t dt. Okay, so what is written here? V prime is, if v is in hs, v prime hs, v prime hs minus 1. Now, if you take u in hs minus 1, then we have here f prime is a smooth function of u is also in hs prime of u hs minus 1. So we have a product of two functions in hs minus 1. For s sufficiently high, it is also in hs minus 1. And then we integrate and return to hs. So this operator, which is written here, is defined for u in hs minus 1 and is continuous from hs to hs and depends continuously on u as element of hs minus 1. Phi u hs hs and depends continuously on u in hs minus 1. Yeah. Now, so this is example. Now, imagine that we can combine operators of this form, composition with smooth function, and linear operators of different kind, differential, pseudo-differential, Fourier operators, and so on. So this way we can obtain nearly all useful operators which use in any application. So this means that this class of operators is quite natural. So in the natural classes of Banach spaces, we have these operators, and they are quite useful. Now I give another definition. With the same Banach spaces, f from x to y is called ruled operator if x can be represented Rm as a union of parallel planes of codimension M, so we have m-dimensional set, m-dimensional family of parallel planes of codimension M. So all the x is foliated in this space, and x on f on x alpha equals, say, f alpha is an affine operator from x alpha to y. Yeah, depending on alpha, continuously depending Rm. Yes. So this means that this map, now we can see that image of each of this plane is also a plane, but they are not anymore parallel. Yeah. So we have this picture, therefore it's called ruled operator. Now,
Which codimension will you?
excuse me?
Which codimension?
Any finite codimension. Yes. So in fact, next definition is f from x to y is called quasi-ruled. You are. If in any bounded domain omega in x, f can be uniformly approximated by ruled operators. Yeah? So it is not ruled itself, but it can be uniformly approximated. Yeah. No example of operator which is not ruled. Operator, say x in x goes to xx. No, x is a Hilbert space. Yeah, just the square of the norm in R is not ruled, quasi-ruled. No, simply because its second derivative in all directions is equal to 2. Yes, so along any line it's already far from any linear function. Yes, so it is not ruled. And now the basic simple problem result is the following. If f is quasi-linear, then f is quasi-ruled. Yeah? So in particular, all useful operators, as I thought, are quasi-ruled. So it is a rather rigid structure. Next is the pair of Fredholm quasi-linear and Fredholm quasi-ruled operators. No, it is more technical. So Fredholm operator which is finite dimensional perturbation of invertible operator, isomorphism between the spaces. Yes. So if in the representation operator phi u is Fredholm for any u, no, with some technical condition of uniformity, then it is called Fredholm quasi-linear operator. If all these operator f alpha in this quasi-ruled, in the definition of quasi-ruled, are Fredholm operators, it's called Fredholm quasi-roulette. And the theorem again, Fredholm quasi-linear entails Fredholm quasi-roulette. Yeah. No, there is some set of more or less obvious theorems about them, like composition of such operators is operator of the same kind, and inverse operator if exists of the same kind. Yes. Now the main, no, the next step. I'm sorry. So if we have the notion of quasi-roulette quasi-roulette map, a quasi-linear map among the mad Banach space or domain in Banach space, we can define quasi-linear manifolds and quasi-roulette manifolds. No, manifolds such that the transition between the charts is given by quasi-linear or corresponding quasi-roulette operators. Yes, and the next result, which is already far from trivial, is that ds is a quasi-linear and quasi-roulette manifold. And the exponent is a Fredholm quasi-linear, the same as Fredholm quasi-roulette map from Vs to ds. Yeah. No, this requires already a lot of technique, which I not. In fact, I find this quasi-linear representation of exponential map, but it requires a couple of lectures to explain in detail how it is done. So let us take it, let us believe it. Yes. Now we have the degree theory for such maps. And this is the point where I have a difficulty for now. So we have the following theorem. Suppose we have some map, say C from M to N, where M, N are quasi linear manifolds. C is a Fredholm quasi-linear map from M to N. Now suppose that C, say, of U0 is F0. Suppose that addition to this M, N are Riemannian manifolds. So there is some metric in M and N. In this case, the metric will be HS metric. So it is a strong metric. And Psi is maps neighborhood U connecting U0 diffeomorphically. Onto a neighborhood f of f0. Yeah, one hand, and other hand.
So that means it's open. It's an open map. I mean, its image is actually.
Yeah, at least in the neighborhood. It's not globally, but in the neighborhood.
In the neighborhood. Slowly.
Yes, and next. Condition that distance in M between U0 and U is less or equal than some function, say omega, of distance in N between phi of U and phi of U0,
Right.
where omega t is positive and omega t goes to infinity as t goes to infinity. So we have, suppose we have such a priori estimate.
P is psi.
Yes.
P
And, excuse me?
P is psi. P is really psi.
Psi.
Do the same.
Yes. So the farther the point, the farther its image. Then psi of M is N. So here all conditions are necessary. If we omit any condition in this theorem, it will fail. And we have in this situation everything but one. We don't have this a priori estimate. So what does it mean, this a priori estimate? So if we return to our flows, so if it fails, then we have to imagine the following situation. We have some flow in on the two-dimensional torus, such that from time to time all the particles return near the initial positions.
Near the initial condition.
Near initial condition with S derivatives. S can be arbitrary. Yeah. So it is really hard to imagine, and it is really hard to prove that it does not happen. Yes, this was the subject of many years of efforts by Viktor Yudovich, and he proved possibly the first real result in this direction, which I would like, if I have one more minute. Yes, I want to finish this example. So what is the idea? If we could find Lyapunov function, what is a Lyapunov function? It is a function, or better to say functional L, no, depending on G and G dot, such that d dt L Ge Gt dot positive. So this Lyapunov function grows along any trajectory. No, in this case, trajectory solution of the Lagrange equation. Yeah? And possibly, if it's even better if it goes to infinity. So Lyapunov function says that a solution can, if we have such a Lyapunov function, and the solution cannot return back. because Lyapunov function is a barrier to it. Yeah. So the question is how to find such a Lyapunov function. So the first example, real example of Lyapunov function, which has some physical meaning, was found by Yudovich, and it looks as follows. So consider the flow of ideal incompressible fluid in a plane domain such that this domain, its boundary contains a piece of x-axis. So it is x, it is y, and the domain is something like this. Now it can be just a square, but certainly it should contain some piece of the x-axis. Now, if we consider a regular solution, that any fluid particle which remained, which started on the boundary, will remain on the boundary. Yes. No, in particular, for some time, it will remain on this straight piece of the boundary, xx. If it is a square, it will remain there all the time. Yeah. And now consider at this particle, which is x of t 0. Yes, consider at this particle the following combination. So omega xt is vorticity. Okay. And consider omega times the omega dx times the omega dy, all this product, at the point x of t 0. Yeah. So we follow this particle and consider this product, and take time derivative. It turns out it is omega square, omega x square at the same point. So it's more or equal than 0. So if initially it was positive, it was non-zero, then it always grows. Yeah. So this means that in H, in some Sobolev space, here we have to consider the functions in a bounded domain. So in the Sobolev space in the bounded domain, we will go farther and farther from the origin here. Yeah. From here, he derived that in fact this goes to both omega x or omega y go to infinity, or both of them. So this was the first and a little bit mysterious and isolated result. No, in his last paper, Yudovich and me and Margulis, we found some extensions of this result. But it remains more or less isolated result, and possibly the breakthrough will come when we find similar Lyapunov functions, not tied to a boundary, but somehow in the holes, in the depth of the fluid. Yes, then it would be more clear what happened. But for now, this is the remaining point, how to prove that any fluid flow which different from staying at rest, the configuration inevitably goes away and does not return. This is very likely, but no proof. Okay, thank you.
So if there did exist such an example where all the particles uniformly came back close to each other,
Yes.
can one see from there what the the point is that is not accessible from the geodesic? I mean, your proof fails, but does such a thing create a counterexample to your conjecture as well?
No, I don't have counterexample. I cannot imagine. If we consider...
Well, let's say there's a counterexample to...
by the way, so it excludes any interesting motions of the points. So if the points, if we take n points, fluid particles, and their trajectories form a braid, then this braid cannot be at long stretch anything but trivial. Yes, so it can't have any interesting twists. So it is for sure, yes. But anything, how to prove that, even if you find a flow where some points really form, no, for example, we have several vortices such they stay in place, for example, yes, then we can take another points, and these points will move, and anyway the distortions will grow here.
But
So
can one see from this example the failure of the two-point problem? Or is that just a separate issue?
no, I think quite opposite. So if we cannot find this example is not counterexample, it doesn't prove anything. Yes, because we follow just a few points in the fluid, yes, and don't know what happens in between.
But maybe this is a question that suppose you have a two-dimensional flow on an infinite two-dimensional space instead of in a torus, then how much of this conjecture would stay then? That, you know, your argument relied on having
You
a
mean
torus.
the whole plane?
Right. I mean, basically it's you have periodic boundary conditions in two dimensions, right? So suppose you don't, then how much of it would stay?
I don't know. I think if we have say, finite energy initial flow, yes, then it will most probably more or less disperse, yes, or several vortices will remain like solitons. And
But maybe that
other
what
will
I'm
go-
asking is related to what he's asking. Because if you have real flow and look at these two segments, you know, then whether you see in your conjecture or you do not, instead of studying it on a torus.
No, torus is a simpler case. Maybe not simpler. No. In the torus, we don't have infinity and we don't have boundary and have little topology. So torus is the simplest. So we have to fight only difficulties with only real difficulties. Yeah? But I don't know. No, I'm strongly convinced that this conjecture is true, that we cannot hold the fluid and all its particles and all displacements and distortions bounded, and any numerical simulation shows that the fluid has very strong tendency to forming high gradients, for example, of vorticity. And it does not return back. It forms, say, fine filaments of vorticity, but they never return back to form something round-shaped. It is. There are so many ways for the fluid to escape that it is just a matter of I don't know, some patience to prove that it really happens.
But does this mean for example, for an open set of final states, you have a geodesic? I mean, can you prove a weaker theorem that for a dense G delta set of second points, you can connect them?
No, yes, yeah, but for an open set, so we have that image is an open set. We have it already.
But an open set in the space of ds, you know,
yes.
that most final points can be reached, and then you're fussing with a set of small category.
No, Possibly we can first prove that there is a dense set of reachable points, and then that is all points. But the spirit of this is to prove that for all of them. No, at least if we, no, I want it to be.
For sure.
Yeah.
Returning to that flow that you showed the
Yes.
rectangles relaxing, but if the final configuration in space is discontinuous.
No, the final is continuous again. So it first falls into discontinuous pieces, then they rearrange somehow, they move inside them, and then they rearrange, and we have this same final configuration as for smooth flow. So it's all happened in between.
When you go from rectangles to hexagon,
Yes. In between, we have not rectangles. In between, these pieces are moving one relative to another. Yeah.
You were saying this variational problem is the same one you were talking about in your talk, when it's frozen in the fluid and you minimize the energy, and at the end you tend to get
Yes,
continuity.
No, it is more or less what happened in your simulations and in our simulations. But we considered just two-dimensional problem, yes? And
Yes.
here we have to take three-dimensional, so many layers of this, many time layers. And so I once discussed this problem with Norman Zabusky. It was about maybe 20 years ago. He said that it's impossible, it requires so much memory. Yeah, but now I think it's possible in clusters. At least I will try.
more questions? Okay, thank you very much.
Thank you.